Okay, welcome back to another week of class. The plan the plan for today is to continue with chapter 7 on factoring, specifically factoring trinomials, so three-term polynomials of this form, x squared plus bx plus c, and maybe some other related forms. Thursday, we're going to move into factoring trinomials of the form ax squared plus bx plus c, where we have a number in front of the x squared. So for Thursday's class, we'll definitely be building off of today's class, and today's class is going to build off of the material we discussed last time in chapter 6 and so on. So make sure you're keeping up with the homework. I would strongly recommend pre-reading section 7.3 for Thursday's class and doing some of the homework for this section before Thursday's class. So I think that'll help Thursday flow a little better. Just kind of a note, factoring is it's kind of like the hump day material of the course. So it's going to be an increase in challenge and difficulty for a lot of students. Some folks, handle it quite well, but you might have to put in a little bit of extra time, a little extra effort, some extra drilling or practice relative to some of the previous sections. So just make sure that you set aside some extra time for that. And, it's one of those things that maybe at first it seems pretty challenging and seems pretty difficult, but after you do 10 or 20 or 30 problems, it starts to become a little easier, a little more natural. So it is one of those things that you just have to actually work with a bit in order to get used to. And to that end, we're going to be solving more problems today than we typically would in an average class. A lot of times I would spend a little more time talking about the strategy, and you'd still have time to work through some problems. But today we're going to be focusing a little more on just going back and forth between the lecture and the worksheet and working through problems. The quotes of the day for today are in honor of the chess candidates tournament that's going on right now, where 8 folks are competing to see who will challenge Ding Liren as for the World Chess Championship. So the 2 quotes from chess GMs, chess grandmasters, one from Emmanuel Lasker, world chess champion for quite a long time in the early 1900s. When you see a good move, look for a better one. And from current GM Maurice Ashley, American GM, there are 3 types of trades: forced, fantastic, and foolish. If it's not forced or fantastic, then it's foolish. And I think both of these hit on the same idea that when there's an important game-changing decision to be made, step back, take a little bit of extra time, a little bit of extra care, and make that decision with that extra care. I think that applies to a lot of aspects of life too. The more significant the potential outcome of a decision, maybe the more carefully it should be made. And maybe we should, what is it? Fools rush in where wise men fear to tread, or something like that. Maybe we should take that adage to heart a little bit. I think that's a little bit of what they're suggesting here. Okay, but jumping into chapter 7. So here we're factoring trinomials of the form x squared plus bx plus c. And our goal is essentially to rewrite x squared plus bx plus c as the product of 2 factors. So we want to rewrite a quadratic, a second-degree polynomial, as the product of 2 first-degree polynomials, x plus m times x plus n. And usually we're thinking that we want m and n to be whole numbers. Now, we recall from before, from chapter 6, that, say, x plus 1 times x plus 2, the product of 2 linear factors. Well, FOIL gives us first x squared. The outers give me plus 2x. The inners plus 1x, or just plus x. And the last give me plus 2. And I can simplify this down to x squared plus 3x plus 2. So sometimes I want to go this direction, but there are other times where if I start with x squared plus 3x plus 2, I want to break it down into the two linear factors. And you can think of this as analogous to with whole numbers. Sometimes we want to do 5 times 2 and figure out that that's 10. Other times we want to maybe be looking at 10 in as one of a set of denominators and break it down into its prime factors. So sometimes we want to go this way, sometimes we want to go that way. So factoring is kind of doing, in a sense, the opposite direction of what we did when we were foiling or multiplying out polynomials. Now let's think a little more about these two pieces up here. So if I try to do this in general for x plus m times x plus n, I see if I FOIL this out, I get my firsts are x squared. My outside is plus nx, inside plus mx, and last is plus m times n. If I look just at my middle two terms, I see that there's a common factor of x in each of those two terms that could be factored out. Think back to section 7.1 for factoring out a greatest common factor. And I'm just going to change, instead of n plus m, I'm going to write it as m plus n. So it's in alphabetical order, I suppose, in the same order as the third term. And I'm equating this kind of to x squared plus bx plus c. So if you gave me x plus m times x plus n, where maybe m was 1 and n was 2, then I could tell you that it's the same as x squared plus 3x plus 2. If we're going the opposite direction, if I start with a quadratic x squared plus bx plus c, and I want to write it as x plus m times x plus n, I would like to have two constraints. If I start with x squared plus 3x plus 2, and I don't know how it factors, really what I'm trying to do is I'm trying to find m and n to make that work. Which numbers do m and n have to be so that it matches up with the x squared plus bx plus c that we started with? So my goal is to find m and n for a given value of b and c. And I see that I have two constraints. I see that m plus n has to equal b, and m times n has to equal c. This almost has the feel of a 2x2 linear system, which we discussed before. If I had something like m plus n equals b and m minus n equals c, that would be exactly the systems that we talked about before, and we solved by graphing, or we kind of briefly discussed some algebraic solution methods too. But this turns out to be a nonlinear system because of this second equation here, m times n equals c. This m times n makes this nonlinear, but it turns out this usually isn't too hard to solve. Our strategy is typically to find some possible solutions keep in mind that we're typically thinking of m and n being whole numbers here, which is super helpful. So we're finding possible solutions. whole numbers. We're finding factors of C. So often what we'll do is we'll just make a list, M and N, and we'll list out some ways that we could multiply two numbers together to get C. And then we'll ask, is it true that for any of these pairings, maybe this one, that their sum also gives me B? So that's really the strategy. And for any of these factoring problems, that's kind of the basic strategy. When you get a little better at factoring, you can kind of take on a guess and check type strategy where you kind of guess an M and N and see if they work. But I wouldn't do that at first. I wouldn't do that in the first, 10, 20, 30 problems. It's really easy to get lost and to say, wait, how do I come up with a good guess? How do I know if a guess is a good guess or a bad guess? You really have to go through a lot of the problems to kind of internalize those patterns. And then guessing and checking can be a little quicker. But I would strongly recommend going through this process for, again, at least, 10, 20, 30 problems, for the problems we do today and most of the problems in the homework. I wouldn't recommend just jumping straight to the guess and check method because before you go through this process and practice it a bunch of times, it's really hard to tell what's a good guess, what's not a good guess. Where is somebody coming up with this certain guess for M and N? So that's tough until you've gone through several problems. But let's take a specific example here. X squared plus 8x plus 15. And remember, the goal is to write this as x plus m times x plus n. And from above, we know that we need to have m plus n equaling, well, x squared plus bx plus c. So b is the coefficient of x. Has to be 8. And m times n, that's the constant term, that is 15. I'm looking for two numbers that multiply to 15 that add to 8. Again, you might be able to just kind of guess the answer, especially for this one. It's not a super tricky one. But we're going to go through carefully just to get practice going through the process. And we'll see that we will sometimes have more challenging ones where the guess and check method would be more difficult. So you might be able to guess and check for a problem like this. But again, I'd recommend going through the process, getting that practice, because it'll be really helpful for the more difficult ones. So what am I looking for? I'm looking for pairs of whole numbers, maybe pairs of integers later on, but for right now, pairs of whole numbers that multiply to 15. Well, the one thing that I could do is I could just start with 1 times 15. I mean, that's certainly a pair of whole numbers that multiplies to 15. And then I could just start increasing m. If m is 2, well, 2 doesn't go into 15 evenly. 3 does. 3 times 5 gives me 15. 4 does not. 5 does, but once I get to 5, I mean, there's nothing special about this ordering of m and n. I could switch the ordering. So 3, 5 is the same answer as 5, 3. So basically, once I get to something like the square root of 15, which is going to be in the ballpark of 4, then I just don't go any further. So this is my listing of all of the whole number pairs that multiply to 15. 1 times 15 and 3 times 5. And now I look through this list of pairs and I ask, is there a set of pairs that also adds to 8? And I do see that 3, 5, those two numbers add to 8 as well as multiplying to 15. So I think my answer is going to be x plus 3 times x plus 5. Of course, multiplication is commutative. This is the same answer as x plus 5 times x plus 3. So if you had chosen to write it that way, no problem at all. But either of these would be our answer. And with these kind of inverse problems, where we're doing kind of the reverse of the more standard operation, it's always a good idea to check your work. So how do we check our work? Well, we just multiply back out. So I FOIL out, I get x squared. My outside gives me plus 5x. Inside plus 3x. And my last 3 times 5, 15. This is 8x for my, what we often call the cross term here. And I see this is my original quadratic. So I got my answer, I checked. I'm satisfied with this answer. Okay, let's do these next 3 problems, and then we'll jump over to the worksheet and practice a couple of them. So you might notice these problems are kind of related to one another. X squared plus 11x plus 18. Here my constant term is 18. X squared plus 9x plus 18. My constant term is also 18. X squared plus 11x plus 30. My cross term is 11x. So how does the feel of the problem change when we change the cross term or when we change the constant term? Let's go through each of these 3 problems. So again, I'm looking for x plus m times x plus n. And we remember that we want m times n to be c, m plus n to be b, where c is the constant term, b is the coefficient of x. So for my first problem, I need a list of factors that multiply to 18. So I'll just start with 1 times 18. If m goes up to 2, well, that works, 2 times 9. If m goes to 3, 3 times 6. 4 doesn't divide into 18 nicely. 5, well, 5 squared is already bigger than 18, so this is our list. Right, if we were to go up any further, if we were to go up to 6, we'd have 6 times 3. We'd be repeating elements of our list. Okay, so I'm looking for one of the lines in this list that also adds to 11. And I see that 2 plus 9 equals 11. So I think this is going to factor as x plus 2 times x plus 9. If I multiply out, first give me x squared. That's the square term that I'm looking for. The outside gives me 9x, a plus 9x. The inside, a plus 2x. That's plus 11x. And my last, give me 2 times 9, or 18. That looks good. How does the process change if I change my cross term, my middle term? If I change this 11 to a 9, what's different? Well, I still have the same constant term. I'm still going to have the same list of possibilities for m and n. Changing my middle term is just going to change which one of these possibilities I go with. Instead of the 2, 9, I'm now going to pull out the 3, 6, because 3 plus 6 is 9, whereas before 2 plus 9 was 11. So if I keep the constant term the same, the constant term is really what drives this full list of possible factors. And what is the middle term doing? The the middle term is saying from this list that's gotten by looking at the constant term, which line am I actually looking for? So I have kind of a list of possibilities that meet this criterion. And then I search through that list to find one that meets the second criterion for the cross term, the middle term, the linear term. But I see this is going to be x plus 3 times x plus 6. And just like before, x plus 6 times x plus 3 is just as valid of a solution. We can check x squared for my firsts. That's good. That matches my squared term. My outside and my inside plus 6x plus 3x, that gives me plus 9x. And my last multiply to give me 18. Looks good. And then what about the third example? If instead of changing the middle term, if I kept my quadratic and linear terms, my first two terms the same, but I changed the constant term from 18 to 30, how does that affect things? Well, this actually affects things quite a bit more, because now my list is going to completely change. I have to rewrite my entire list. So now I'm looking for two numbers to multiply to 30, like 1 and 30, 2 and 15, 3 and 10. And if 4 doesn't work, 5 times 6. And if I go any further to 6, I get 6 times 5. That's a repeat. Again, the order of m and n doesn't matter. So these are all of the whole number pairs that multiply to 30. And then I want to find the one that adds to 11. And I see that 5 and 6 seem to work. And again, checking, we get x squared plus 6x plus 5x. That's plus 11x plus 30. That looks good. So the constant term is what decides what this list looks like. And then the linear term, this b, this coefficient of x, is what picks out which line from that list I'm going to go with. Okay, so let's work through these 4 problems. These are kind of similar in vein to the ones I just did, kind of a warm-up one that's a bit easier, and then a few problems that might be a little bit more challenging. So take a look through these, try to work through them. I'll give you about probably about 6 minutes to work through these 4. So for each of these, again, go through, write out your list, write out all of the terms in the list, find the one that matches the cross term, and then also check at the end. So that's an important step to get used to in factoring, is to check at the end. So we'll take about maybe 5 minutes or so for these 4 problems. Okay, so looking at this first one, actually the first two are pretty straightforward. If I look at my constant term 7 here, there's actually only one way to factor it, right? 1 times 7. 7 is a prime number. So 1 times 7 is obviously 7, but 2, 3, 4, whatever else aren't factors of it. So really, I only have one candidate for M and N, and that's 1 and 7. And is it true that 1 plus 7 equals 8? Yeah, that is true. So I see that this factors as x plus 1 times x plus 7. And I can FOIL that check, and it is right. Similarly, for the next one, 13, a little bit bigger of a number. But again, there's only one way it factors. 1 times 13, 1 plus 13 is 14, so pretty similar problem. What about a number like 21? Well, I could get 21 by multiplying 1 times 21. 2 doesn't go into 21. 3 does. 3 times 7. 4, 5, they don't go into 21. So it looks like I have two choices, 1 and 21 or 3 and 7. And I'm looking for the sum to be 10. So obviously that's going to indicate that 7 and 3 or 3 and 7 is the right way to go. So this gives me x plus 3 times x plus 7. And again, I can check it by multiplying out. My first give me x squared. My outside gives me plus 7x. Inside plus 3x. So that gives me a total of plus 10x. And then my last 3 times 7 do give me 21. So that looks good. And then the last problem here is a bit more complicated. 48 has a lot of factors. So let's just start with 1 times 48 and then work our way up, incrementing up by 1 as we go down the m column. 2 is a factor of 48, 2 times 24. 3 actually is. If we remember our divisibility rules, a number is divisible by 3 if the sum of its digits is divisible by 3. 8 plus 4 is 12, and we know that 12 is 3 times 4, so we know it's going to be divisible by 3, and we figure out that it's 3 times 16. Is it divisible by 4? Is it divisible by 2 twice, basically? Yes, it is. It's 4 times 12. Divisible by 5? No, it doesn't end in a 5 or a 0, so it's not divisible by 5. Is it divisible by 6? Is it divisible by both 2 and 3? And yes, it is. It's 6 times 8. Then, of course, we could maybe try going up to 7, but we see it's not divisible by 7. And if we went up to 8, we'd be repeating the 6 and 8. And now I'm going to look through this list and try to find an entry that adds the 14. And I see that 6 and 8 add to 14, so I end up with x plus 6 times x plus 8. I want to check this, so I multiply out. First, give me x squared. My outside gives me plus 8x, inside plus 6x, that's my plus 14x. And then my last 6 times 8 is 48. So that looks good. Any questions on these ones? So we already kind of noticed a pattern that when we have a prime number at the end, it seems like things are a bit easier. And when we have a number with a whole lot of factors, like 48, our list gets a little bit longer and it takes a little more time to write out. Okay, let's look at these next few problems. So the strategy is really going to be the same here. We have our constant term is 60. And I'll just start with 1 times 60. It's always good to start here because this is also an easy factor to forget. It's easy to forget that you can write a number as 1 times itself. But if you just kind of start by saying, what's the smallest number I could pick for M? 1. So I always end up writing that 1 times the constant. 1 times 60 is 60. Does 2 go into 60? 2 times 30. 3 times 20. 4 times 15. 5 times 12. 6 times 10, right? There's 60 has lots and lots of factors. 7 doesn't work. 8 doesn't work. 9 doesn't work. And if we went up to 10, we'd repeat 10 and 6. So we can either go up to something like the square root of the number, or we can just kind of think through until we get to a point where we've repeated. So this is our list of the whole number factors of 60. And what am I looking for? I'm looking for one that adds to 19. So 60 and 1 doesn't work. 30 and 2 doesn't work. 20 and 3 doesn't work. Okay, there we go. 15 and 4. 15 plus 4 is 19. Here my variable is y, so I'll just respect that in the answer, but I could write y plus 15 times y plus 4, or I could write y plus 4 times y plus 15. Again, both are equally valid. I could FOIL out, I get y squared plus 4y plus 15y is plus 19y. And then plus 15 times 4 is plus 60. So that looks good. And that would be my answer. Okay, let's look at x squared plus 4x plus 18. So I need two numbers that multiply to 18. So I start with 1 and 18, 2 and 9, 3 and 6, 4 doesn't work, 5 doesn't work, 6 is a repeat. Looking for two numbers from this list that add to 4. 18 plus 1 is 19, that doesn't work. 9 plus 2 is 11, that doesn't work. 6 plus 3 is 9, that doesn't work. Well, I made an exhaustive list of all pairs of factors that multiply to 18. This is all of them, pairs of whole number factors. And none of those pairs add to 4. What does this mean? Essentially, this means that I can't factor this. We call this a prime polynomial. A very easy example of a prime polynomial is something like x squared plus 1. Or in other words, x squared plus 0x plus 1. We're looking for two numbers that multiply to 1, which is only 1 and 1, and then add to 0. And of course, 1 plus 1 is not 0. So there are polynomials that you can't factor, at least not that you can factor in over the whole numbers or over the integers like this. Now, could we find two numbers, m and n, maybe fractions, maybe rational numbers? Could we find two numbers, m and n, that multiply to 18 and then add the 4? Yeah, we probably could. We have 2 degrees of freedom, 2 things we can pick, and we have 2 constraints, multiply to 18, add to 4. We probably could find such an m and n, but they wouldn't be whole numbers. So we call these kinds of polynomials prime because they don't factor into x plus m times x plus n, where m and n are whole numbers, or later on could be integers. So they're not positive or negative whole numbers. And this is analogous to how some numbers, I mean, if we take 18, for instance, we can factor 18 like 2 times 3 times 3. But if we take a number like 7, it's kind of just itself. Right? So this calling this a prime polynomial is kind of analogous to the idea of a prime number. This quadratic can't be broken down into linear factors, at least not in a nice way that uses integers. Okay, let's work through one more problem and then do some practice. So here we have another example, x squared minus 9 plus 18. So I'll list my factors that multiply to 18. I've already done that up here, so I'll just copy it down. And now I have an interesting question. I'm looking for two factors that add to negative 9. So far, I've only dealt with positive coefficients. All of my numbers that have come up have been positive. All of my terms have been added together. I have a little bit of a monkey wrench thrown in here. I have a term that has a minus sign in front of it. How does that change things? Well, is this really the only set of three pairs that could multiply to 18? Well, I know if I have a negative times a negative, that also makes a positive. So I actually could have plus 1 times plus 18, or I could have minus 1 times minus 18. I could have plus 2 times plus 9, or I could have minus 2 times minus 9. And similarly, I could have plus 3 times plus 6, or minus 3 times minus 6. To make a positive 18, the magnitude of m and n have to either be 1 and 18, 2 and 9, or 3 and 6. But the sign could both be positive or both be negative. So I actually kind of have 6 choices to choose from here. So do I have an option that I can add together and get negative 9? Well, yeah, I think negative 3 plus negative 6 makes negative 9, and negative 3 times negative 6, the negatives cancel. 3 times 6 is 18. So I think this is going to be, what would I say? Something like x plus negative 3, but that's really just x minus 3. And x plus negative 6 is really just x minus 6. I want to check this, so I multiply out. Firsts give me x squared. My outside's minus 6x, my inside's minus 3x. That gives me a net minus 9x. And then my last, minus 3 times minus 6, negatives cancel and give me positive 18. So that does look good. So again, building up a little bit of complexity here, we could get something that factors nicely. We could get something that doesn't factor at all, like this. Or when we start allowing for negative signs, either subtraction in our terms or subtraction in either of our terms, we have to kind of adjust a little bit what our list might look like. We have to account for the fact that we kind of ignored up here that there are products of negatives that could also give me a positive constant term. Okay, so let's look at these next 4 problems, and these are all kind of variations on a theme. You see they all have the constant of plus 100, but they have different linear terms. So take a look through these 4 problems. Maybe again, take about maybe about 4 minutes, because it's the same constant, so you can kind of use more or less the same list to work off of. for each of these four, but let's take about 4 minutes. Again, go through the process carefully. I wouldn't recommend using guess and check at this point. Carefully go through the process, look at each of these, decide how it factors or if it factors. We saw that there's a possibility that we don't get a nice factorization. So take about 4 minutes, look at these, and then we'll discuss the answers. Okay, let's discuss the answers. As always, we're just learning this material. If you got a little stuck, if you didn't get through all the problems, don't worry about it. Um, But here we write out our list of factors. So we always start with 1 times 100, or 1 times our constant. 2 goes into 100, 3 does not, 4 does, 5 does, 6, 7, 8, 9 do not, and 10 does. Then we get 10 times 10, so clearly we can't go any higher than that, or we would start repeating. And we want to remember that to multiply to positive 100, we could have a positive m and a positive n, or a negative m and a negative n. So I have 2 options for each of these lines, 2 positives or 2 negatives. They have to have the same sign to multiply to a positive, but that sign can be both positive or both negative. So I really have 10 options here. For my first one, I'm looking for m plus n is positive 101. So since my middle term is positive and both have to have the same sign, I know that I'm looking for elements from this list that are both positive. And that suggests 1 in 100. 100 plus 1 is 101. Or this gives me x plus 100 times x plus 1. I can check, and that looks good. My next problem, x squared plus 20x plus 100. Again, I have the same list I'm working off of, these list of factors for 100. I keep in mind, again, that they have to have the same sign, so both positive or both negative. And here the cross term is positive, so I'm only considering the both positive scenario. And I'm looking for 2 positive numbers that multiply to 100, 2 positive numbers from this list that also add to 20, and that's clearly 10 plus 10. So I get x plus 10 times x plus 10, or I could write that a little more conveniently as x plus 10 all squared. Remember, x plus 10 squared is not x squared plus 100. We have to be careful and FOIL it out. That's where that plus 20x comes from. What about x squared minus 20x plus 100? Again, same list of factors for 100. But now I'm looking for a negative cross term. I'm looking for a minus 20x. My m and n have to have the same sign. They have to both be negative now. So I'm looking for 2 numbers from this list that when I make them negative and add them together, I get negative 20. And that's clearly negative 10 and negative 10. Or x minus 10 times x minus 10 is my factorization, or x minus 10 all squared. If I multiply out, my first give me x squared. Outside gives me minus 10x. Inside gives me another minus 10x, so minus 20x. And my last give me negative 10 times negative 10 is positive 100. So that looks good. And then my last problem, again, I have a positive constant term, which means the 2 things I'm multiplying together have to have the same sign, both positive or both negative. I have a negative cross term, which tells me that my 2 things I'm looking for are both negative. So I'm looking for 2 negative numbers that multiply to 100 and add to negative 52. That's going to be negative 2 and negative 50. So x minus 2 times x minus 50 is my factorization. And if I check it, I get x squared from the firsts, from the outer minus 50x, inner minus 2x, that's minus 52x. And then minus 2 times minus 50 is plus 100. That looks good. Are there any questions on any of these problems? Okay, let's work through. I thought I had 2 more at the end here. But I had 2 more after this. Did I put them on the wrong sheet or something. I had a couple like this at the end of my lecture, but they've somehow disappeared, so I'm not exactly sure how. I wonder if I put them on, did I put them on this one? Nope. All right, well, the mysteries of Microsoft products. I might have to make up a couple at the end here, but okay, so the kind of last topic in this section anyway, before we get to the ones that somehow have disappeared. Now what does the situation look like if our constant term is negative? I'm looking for two numbers that multiply to -12 and that add to +4. Well, my basic strategy stays the same. I start by listing my factors m and n that multiply to 12. I start by just basically ignoring the sign. 1 and 12, that works. 2 and 6, 3 and 4. These are the three options for getting two whole numbers that multiply to 12. But then I note that m times n is -12, which means they have to have opposite signs. So I have +1 associated with -12, or -1 associated with +12. +2 with -6, -2 with +6, +3 with -4, -3 with +4. I have 6 options here, just like before when I accounted for the pluses and minuses, I doubled the number of options. But here I absolutely have to account for the plus and minus, right? There's no way around it because one is going to be positive, the other negative. So these have to have opposite signs, one positive, one negative. And I'm looking for a member of this list that adds to +4. So really what I'm looking for is I'm looking for a difference that looks like 4. The difference between 1 and 12 looks like 11. So whichever way I arrange the pluses and minuses, I'm going to get something that's like a +11 or -11. And that's not the right line. The difference between 4 and 3 is 1. So depending on how I have the positive negative set up, I might get a +1, maybe a -1, but certainly not a +4. But 2 and 6, that does look like a difference of 4. Okay, so now do I want +2 -6, or do I want -2 and +6? Well, I have a +4. So net, I have a positive. That means the plus sign has to be attached to the bigger number. So I need to have +6 and -2. +6 and -2, they do have opposite signs. They multiply to -12, and they add to 4. So I think that's my that's my choice from this list of 6 options. We did a lot of work there. Let's double check. Our first give us x². That's good. Our outer gives us -2x. Our inner +6x. That gives us a net +4x. We want to be especially careful to make sure we get that plus minus right. It's easy to pick the wrong sign and make it x -6, x +2, and end up with a -4x, but we didn't make that mistake. And then our last give us +6 times -2, -12. So this looks good. So if we have coefficients that are all positive, It's pretty straightforward. We just make our list. We don't really have to worry about the signs because a positive constant coefficient means that it has to be the same sign, and a positive cross term, a positive linear coefficient, if I can select it here, tells me that both signs have to be positive, because if both signs were negative, obviously negative plus a negative is going to be a negative. So this is kind of the simple case. If we have a positive constant term and a negative cross term, and not too bad, we just kind of make our same chart like before, and these have to have the same sign. So both positive or both negative. Because my cross term is negative, they both have to be negative. Because if I add the two positives together, I get a positive, not a negative. When my constant term is negative, then I know that I have to have one of my factors being negative, one of them being positive. And I have to figure out which one works best with my cross term, right? The way that I kind of pare this down step by step is I look at the size of my cross term, that's a 4, and I look at my list here, and I look for a line that gives me a difference of 4. Like 1 and 12 have a difference of 11, 3 and 4 have a difference of 1. Neither one of them is going to work. 2 and 6 have a difference of 4. And then I have to figure out, I need one of these to be positive, one negative. Which one gets the positive? Well, the positive, if I can select it, the positive coefficient here tells me that net, I have to end up with a positive number. The positive has to go on the bigger of the two numbers. So we have plus 6 minus 2, so that I end up with a plus 4. Okay, what about a problem like this? X squared minus x minus 20. So I'm looking for two numbers that multiply to 20. So we'll just start there. We have 1 and 20, 2 and 10. 3 does not divide evenly into 20. 4 and 5. And then if we went up any more, we get 5 and 4. We repeated, so we can stop here. I know that m times n is negative 20, so m and n have to have opposite signs. So I could have plus 1 times minus 20, or minus 1 times positive 20, plus minus, minus plus. And you don't necessarily have to write in all of these pluses and minuses. You can keep it just kind of in the back of your mind, but I'm writing them in here just for illustration. And then what am I looking for? I'm looking for m plus n to be negative 1. I'm looking for a difference that looks like 1. That's not going to be 20 and 1 or 10 and 2. Those have differences that look like 19 or 8. But 5 and 4 seem to work. The sum has to be negative 1, so I have to have a net negative, which means the bigger number has to have a minus attached to it. So I think minus 5 and positive 4 are the two numbers I'm looking for. Negative 5 plus 4 gives me negative 1. Negative 5 times 4 gives me negative 20. That should work. And if I check, my first give me x squared. I get plus 4x minus 5x is minus x. And then minus 5 times minus 4 is negative 20. So that works out. Okay, let's come over to the worksheet and we'll work through these Next two sets of problems here. I'll try to get them all on the screen, but we'll first focus on these three problems. We'll take about 4 minutes to work through these three problems. And then we'll come back and discuss. If you want to, you can work ahead a little bit to these ones, but work through these three problems. Make sure to carefully check your answer at the end, including checking the signs. So it'll take about 4 minutes for these first three problems. Okay, let's discuss these three. So for the first one, we're looking for two numbers that multiply to -6, add to -5. And here I see I have 1 times 6 and 2 times 3 that multiply to 6. I want a product of -6, so these have to have opposite signs. So I'm looking for a difference that looks like 5. So I'm looking at the 1 and 6 line, and I want to end up with a -5. So I know the negative has to be attached to the bigger number. So -6 plus 1 equals -5. So here I think I factor into y minus 6 times y plus 1. Let's check that. Our first give us y squared. Our outside gives us plus 1y. Our inside minus 6y. So that's minus 5y. And then minus 6 times plus 1 is minus 6. So that looks good. Note that it's kind of easy to make a mistake here. If we had kind of forgotten to note that we need opposite signs, we could have done something like, oh, well, -2 plus -3 is -5, right? And mistakenly put down, say, y minus 2 times y minus 3. Our first would have worked out, right? Our outside and inside would have given us minus 5y, but our last, if we're careful with the signs, would actually give us plus 6 instead of a minus 6. So we see this wouldn't be right. But this is a problem that could easily go wrong if we don't take care with those signs. If I look at my next problem, x squared plus x plus 5, I see that to get 5, well, 5 is a prime number. I can just have 1 times 5. These have to be the same sign, so either plus 1 times plus 5 or minus 1 times minus 5. And I'm looking to add to get 1. And again, plus 1 plus 5 is positive 6, minus 1 minus 5 is negative 6. None of those give me a plus 1. This polynomial is prime. We can't factor it into a product of linears. It just kind of like is what it is. And then my third example here for 8, a perfect cube, we have 1 times 8, 2 times 4, 3 doesn't go into 8, 4 times 2, but that's a repeat, so we're done. We see that we have a negative sign. We need to multiply to -8, so we need to have opposite signs. I've stopped writing out all of the signs explicitly, but I'm looking for m plus n equals -2. With opposite signs, when I add together, I'm naturally taking a difference. So the difference between 1 and 8 looks like 7, not like 2. The difference between 2 and 4 looks like 2. That seems like it'll work. I need to have the sum being negative, so I need to have the negative sign on the bigger number, the positive on the smaller. So I think 2 plus -4, if OneNote would stop correcting my 4s to 9s, 2 plus -4 does give me -2 and does multiply to -8. And then again, if I check being super careful with the signs, my first give me x squared, that's good. My outside minus 4x, inside plus 2x, so -4 plus 2 is -2. And then my last 2 times -4 is -8. So that looks good. Okay, let's work through these. Next two problems will take maybe about 3 minutes for this and then come back and discuss. So take about 3 minutes, work through these, and we'll go through the solutions. Okay, let's work through these answers. So for this first one, x squared minus 3x minus 54, we first look for the factors of 54. So 1 times 54. Does 2 go into 54? Yeah, it does. It's an even number. 2 times 27. Does 3 go into 54? Yeah, we can either see that 27 is a factor of 54 and 27 is 3 cubed, or we could see that 5 plus 4 is 9. Since 9 is divisible by 3, 54 is divisible by 3, and we can work out that 54 is 3 times 18. Does 4 go into 54? Or does 2 go into 54 twice? Well, no, because it's 2 times 27, and then 27 doesn't have any other factors of 2 left to move from the n column to the n column, or from the n to the m column. So 4 does not, 5 does not, it doesn't end in 5 or 0. What about 6? Yeah, it has a factor of 2 and a factor of 3. So 6 times 9 is 54. 7 or 8, nope. And then if we get up to 9, we've repeated 9 times 6. We know that we have to have opposite signs to multiply to get a negative 54. So we're interested in when the difference in the entries in the columns looks like 3, looks like our cross term. It's negative 3, but we're just looking for a 3 to start with. 54 and 1, 27 and 2, 18 and 3, none of them do it, but 9 and 6 looks promising. And then specifically, I need the sum of the two numbers that I picked to be negative 3. So I need the negative attached to the bigger number. So negative 9 plus positive 6. Negative 9 times positive 6 gives me negative 54. Negative 9 plus positive 6 gives me negative 3. And there's my factorization. X minus 9 times x plus 6. And the next problem, x squared plus 4x minus 12. Again, I start with the same process. I look at 12, find its factors. 1 times 12, 2 times 6, 3 times 4. If I go up any more, 4 times 3, I've repeated. So I've listed everything. I see that I want to multiply to get a negative 12. So these have to have opposite signs. So I'm looking for a difference that looks like 4. 12 and 1 differences look like 11. 4 and 3 difference looks like 1. But 6 and 2, the difference looks like 4. Specifically, I need a positive 4, which means the minus sign has to be attached to the smaller number, the positive sign attached to the bigger number. So I have to have negative 2 plus 6 gives me positive 4. Negative 2 times 6 gives me negative 12. And again, if I check, my first give me x squared. That's good. My outside gives me plus 6x, inside minus 2x. That gives me a plus 4x, so the sign works and everything. And then the last give me minus 12. That looks good. Okay. And then, like I said, I don't know where my 2 went from the lecture slide here, but I came up with 2 in the meantime. So I'm just going to paste this over and then change the numbers around a little bit. And we'll go through 2 examples here and then work through 2 examples in the practice bit. So just give me a second to type all these in. Okay, so what if I have a trinomial that looks like this, that has more than one variable in it? X squared plus 5xy plus 6y squared. What kind of a structure would lead to a trinomial like this? Well, if I have something like, x plus y and let's say x plus 2y, something like that. If I FOIL this, what do I get? My first give me x squared. My outside gives me plus 2xy. My inside gives me plus yx, or that's just the same as plus xy. And my last give me plus 2y squared. So you get x squared plus 3xy plus 2y squared. So interesting question. What if I didn't have the y's here at all? If I didn't have any y's, I kind of know how to do my factoring step. If I have y's that are in this kind of a pattern in my polynomial, I mean, it seems like the factorization is going to work pretty similarly to what we did before, right? I don't have like all kinds of different factors of y everywhere, but specifically in each term, I have two factors of a variable. In the first term, I have two factors of x. In the last term, I have two factors of y. And in the middle term, I have one factor of x and one factor of y. So I don't have something like, x squared times y cubed plus, 3xy squared plus 2y or something like that. I have two factors of a variable in each term, two factors of x, two factors of y, or one factor of x and one factor of y. So it turns out that this factorization is going to work pretty similar to before. I just know that I'm going to end up with an end result that looks a little more like this. So let me just erase these so I have a little more room to work with. So if I just kind of ignore the y's just for the time being, I'm looking for two numbers that multiply to 6, like 1 and 6, or 2 and 3. There's a positive there. These have to be the same sign. And they have to add to positive 5. So they have to be both positive. Or I'm clearly looking for 2 plus 3, which gives me 5, and 2 times 3 gives me 6. So if the y's weren't here, I would think I'd have like x plus 2 times x plus 3, and that would be it. But with the y's in this configuration, I see that this is just x plus 2y times x plus 3y. If I check, my firsts give me x squared. My outsides give me plus 3xy. My insides give me plus 2xy, so that's a net plus 5xy. And then my last give me 2 times 3 is 6, times y is y squared. So again, when I have more than one variable in a polynomial, and when it fits this really nice pattern, where each term has two factors of a variable, two factors of x, or two factors of y, or one factor of each x and y, then I can kind of just factor like I've been factoring polynomials with one variable. And similar thing down here. Here we have variables a and b, but same idea applies. I see if I ignore the b, then I have like a squared minus 4a minus 12. I'm looking for two numbers that multiply to -12. So let's just start by getting our factors of 12, 1 and 12, 2 and 6, 3 and 4. I need them to multiply to -12, so they need to be opposite signs. I'm looking for a difference that looks like 4. Not this, not that, but something to do with 2 and 6. And specifically, I need a -4. So -6 and +2. Again, if the b's weren't here at all, if this was just a squared minus 4a minus 12, I think this factors into a minus 6 times a plus 2. And with the b's, if I just stick a b in there like this, does that work? My first's a squared. My outside's 2ab plus 2ab. Inside's minus 6ab. That's a net minus 4ab. And then my last, minus 6 times plus 2 is minus 12. B times b is b squared. Now, kind of a side note, you might ask yourself, well, I chose to kind of pretend the b's weren't here. So I chose to kind of treat this like a squared minus 4a minus 12 and go this route. Why didn't I choose instead to pretend the a's weren't there, other than the fact that the a's are written first? If I pretended the a's weren't there, I'd get what? 1 minus 4b minus 12b squared, or I'd get, minus 12b squared minus 4b plus 1. This is also just the quadratic in b. But notice that this is going to be a more challenging problem because the coefficient of b squared is not 1. Our current section is kind of the easier set of trinomials where the coefficient of the quadratic term is always 1. Right? In all of these problems that we've done, the coefficient of the square term has always been 1. So if we look back up through any of these problems, that's what we see. Section 7.3 builds on this section and says, what do we do if the coefficient of the quadratic term is not 1? So which variable did I choose to kind of ignore for a little bit of time? I chose to ignore the one that was attached to a coefficient that was not 1, and I chose to keep the variable where the second degree bit was attached to a coefficient of 1. Okay, so for the last few minutes, let's work through these two problems. Again, pretty similar problems, pretty similar setup. So take about maybe 4 minutes, work through these two problems, then we'll come back and discuss. Okay, it's just about 4 minutes, so let's take a look at these. So first we have x squared minus 8xy minus 65y squared. And again, we're just going to kind of, at first, kind of pretend the y's aren't there. So we're kind of thinking in terms of x squared minus 8x minus 65. So I first want to look at my constant term, so to speak, my 65, and find its factors. I have 1 times 65 gives me 65. 2, 3, and 4 don't go into 65. 2 and 4 because it's not even. 3 because 6 plus 5 is 11, which is not divisible by 3. So it fails that divisibility test. Or because we note that 60 is divisible by 3, and then 5 more, that 5 is not divisible by 3. 5 does go into 65, and we get 5 times 13. We note that these are 2 primes. We're not going to have any other factors. There's no other way to factor this because we factored into 2 primes. We could go 6, 7, 8, 9, 10, 11, 12. None of those would go into it because there's no other primes to kind of swap back and forth between the m and n columns. We note that we're looking for a negative 65 for the so-called constant term. We need opposite signs. And our cross term looks like 8, so we're looking for a difference of something that looks like 8. 65 and 1 is certainly not going to do the trick, but 13 and 5 looks promising. And in particular, I want minus 8, so the negative has to go on the larger number. So negative 13 plus 5 gives me minus 8. And then again, if I forgot about my y's, I would just have x minus 13 times x plus 5. But with my x's and y's in this specific pattern, I notice that I can just kind of tack on a y onto my constant, and I'd get x minus 13y times x plus 5y. Let's carefully check that everything went right. Oh, I erased a little bit of my y's there. So if I do my FOIL, my first give me x squared, my outside gives me plus 5xy, my inside minus 13xy, that's a net minus 8xy, that looks good. And then my last, I get minus 13 times 5 is minus 65 times y squared, that looks good. And then similar process for the last problem. A squared plus 3ab minus 28b squared. I'm going to kind of pretend the b's don't exist because the a's are the ones with the coefficient of 1 on the quadratic term. So I'll treat the 28 like a constant term. What are the factors of 28? 1 and 28, 2 and 14, 4 and 7. I know I eventually want a negative 28, so these have to have opposite signs. And I'm looking for a difference that looks more or less like 3. 1 and 28, 2 and 14 don't really fit the bill, but 4 and 7 look promising. And specifically, I want a positive 3. So I want the negative attached to the smaller number, the positive attached to the bigger number. Negative 4 plus 7 equals 3. So I kind of build up my solution one piece at a time, right? I start looking at the absolute value of the constant term, then getting the signs right. Do I need same or opposite signs? Then looking at the size of the cross term. I need a difference of something that looks like 3 to select my line, and then the sign of the cross term to get my sign on the right piece. And again, if I forgot about the b's, I would be looking at a solution that looks like a minus 4 times a plus 7. And then I just kind of slot my b's in where I know they go in this pattern. A minus 4b times a plus 7b. And if I multiply out, I get a squared plus 7ab minus 4ab. That's a plus 3ab. That looks good. And then minus 28b squared. That all looks good. Okay, any questions on anything from today?